Our cities are giants built of concrete. The skyscrapers, the roads, the bridges, the tunnels. They are the bones and arteries of modern civilization. But these concrete structures, which seem so permanent, are constantly under attack from time and the elements. They crack, they weather, they decay. Every year, we spend billions of dollars and generate massive carbon emissions just to patch up our crumbling infrastructure. It's a never-ending, costly battle. But what if our cities could heal themselves? What if a crack in a bridge could mend itself, just like a cut on your skin? This isn't science fiction. This is the incredible promise of bioconcrete, a revolutionary material that is literally alive. So what is this living concrete? At its heart, bioconcrete is a masterpiece of biomimicry, that is, innovation inspired by nature. It has the amazing ability to automatically seal its own cracks, stopping water from seeping in and corroding the steel reinforcement that holds everything together. The secret ingredient? Bacteria. The idea started taking shape in the early 90s, but it was a microbiologist named Henk Jonkers at the Delft University of Technology in the Netherlands who really brought it to life in the mid-2000s. He and his team developed a bioconcrete that mixes in special, limestone-producing bacteria. These aren't just any bacteria. They are hardy survivors, capable of lying dormant inside the harsh, alkaline world of concrete for up to 200 years. Here's how the magic happens. The process is called microbially induced calcite precipitation, or MICP. Imagine a tiny crack forming in a concrete wall. As water inevitably finds its way into this new opening, it acts like an alarm clock, waking up the dormant bacterial spores embedded in the concrete. Once awake, these bacteria get hungry. And luckily, the creators of bioconcrete pack them a lunch, a nutrient source, usually something called calcium lactate. The bacteria start feasting on this calcium lactate, and through their metabolic process, they convert it into calcium carbonate. You might know calcium carbonate by its more common name, limestone or calcite. This newly created limestone crystallizes and fills the crack, sealing it shut from the inside out. It's almost exactly like how a scab forms over a wound to heal your skin. Of course, you can't just toss any old bacteria into a cement mixer. The microbes have to be tough enough to survive a pH level of 12 or 13 and the intense pressures of mixing. That's why researchers favor spore-forming bacteria from the Bacillus genus. Strains like Bacillus subtilis and Bacillus conii can form tough little spores that protect them, keeping them viable for decades, even centuries, until they're called to action by a crack. But even these tough spores need protection during the violent concrete mixing process. To solve this, scientists have developed clever encapsulation techniques. Think of them as tiny protective life pods for the bacteria and their food. These pods are strong enough to survive the mixing, but brittle enough to break open when a crack forms, releasing the healing agents right where they're needed. Some methods use porous clay aggregates to house the bacteria. Others use tiny hydrogels, which are water-absorbent polymers that not only protect the bacteria, but also hold onto the moisture needed for them to do their job. This self-healing mechanism is remarkably effective, capable of sealing cracks up to 0.8 millimeters wide. For comparison, regular concrete can only self-heal tiny cracks smaller than 0.2 millimeters. The journey to create bioconcrete has been a long one. As I mentioned, regular concrete has a very limited, natural ability to heal itself called autogenous healing. This happens when unhydrated cement particles react with water in a crack. But it's a slow and weak process, only good for the tiniest fissures. Researchers knew they needed something better. After early explorations with self-healing polymers in the 90s, the focus shifted to biology, inspired by nature's own efficient repair systems. Henk Jonkers' breakthrough at TU Delft was the turning point. His team's success led to the construction of the world's first building using bacterial self-healing concrete, a vital real-world test that provided invaluable data. Since then, the field has exploded. Universities and companies around the globe are refining the technology, searching for new bacterial strains, and creating better ways to deliver the healing agents. This research has already spawned commercial companies. A spin-off from TU Delft called Green Basilisk now sells a healing agent that can be mixed into new concrete or even applied as a liquid to repair existing structures. Another company, Biomason, takes a slightly different approach. They use bacteria to literally grow bricks at room temperature, completely skipping the energy-guzzling firing process of traditional brickmaking. Their biological cement creates bricks just as strong as conventional ones, but with a tiny fraction of the carbon footprint. These aren't just lab curiosities anymore. They are real products being used in real construction projects. So where's this technology being used? One of the most famous examples is a lifeguard station in the Netherlands. Built in a harsh coastal environment with constant exposure to wind and salt water, it was the perfect place to test bioconcrete's durability. The results have been incredible. The structure has shown remarkable longevity, needing minimal repairs over a long period, proving its resilience against corrosion. In another case, a liquid bacterial repair system was used on a series of cracked concrete floor slabs. The traditional solution would have been to demolish the slabs and pour new ones, a hugely expensive, disruptive, and carbon-intensive process. Instead, the cracks were treated with the bacterial agent. Over time, the bacteria woke up and went to work, sealing the network of cracks and making the floor watertight again. An analysis of the project showed a life cycle cost reduction of about 33% and, even more impressively, a 90% reduction in CO2 emissions compared to the old method. Similar results have been seen in projects on airport pavements, where the bacterial treatment was estimated to extend the pavement's life by 15 years, avoiding a costly rebuild and slashing repair-related carbon emissions by over 90%. The potential applications are vast. Imagine bridges and tunnels that heal their own cracks, reducing the need for dangerous and expensive inspections and repairs. Highways that mend their own potholes, minimizing traffic jams. Buildings that are more sustainable and resilient, even improving their own insulation by sealing air leaks. Water treatment plants and pipelines that prevent their own leaks. And marine structures like seawalls and piers that can better resist the corrosive power of salt water. The technology has even been explored as a gentle way to restore historical monuments made of limestone. This all sounds amazing, but you're probably thinking about the price tag. And you're right, that is a major consideration. Right now, bioconcrete is more expensive to produce than traditional concrete, anywhere from 30% to 100% more, sometimes even higher. The extra cost comes from cultivating the bacteria, the nutrient packets, and the encapsulation process. One estimate puts a cubic meter of bioconcrete at around €200, compared to about 75 to 100 euros for standard concrete. But looking only at the initial price is short-sighted. The true economic genius of bioconcrete is revealed when you look at the entire life cycle of a structure. This is called a life cycle cost analysis. The ability to autonomously repair cracks leads to huge long-term savings. Think about it: drastically reduced maintenance and repair costs, which in some countries account for nearly half of all annual construction spending. You also get a significantly extended lifespan for the structure. If the bacteria can remain viable for 200 years, buildings and bridges could last much, much longer, avoiding the colossal expense of replacement. And for critical infrastructure, less downtime for repairs means less economic disruption from things like traffic closures. When you factor in all these savings, that higher initial investment starts to look very, very smart. Of course, the path to making bioconcrete a global standard isn't without its hurdles. The high initial cost is still the biggest barrier. We also need to figure out how to scale up the production of bacterial spores and encapsulation materials to meet the massive demand of the global construction industry. While lab tests are promising, we still need more long-term data from real-world structures to prove the bacteria remain viable and effective for many decades. The healing process also depends heavily on the environment. It needs moisture to work, so its effectiveness in very dry climates could be limited. There are also some conflicting studies on whether adding the bacteria affects the concrete's mechanical strength, though encapsulation methods seem to solve this by keeping the bacteria separate from the primary concrete matrix. Finally, like any new material, bioconcrete needs standardized testing protocols and building codes before it can be widely adopted by engineers and architects. Overcoming these challenges will take a coordinated effort, but the work is well underway. The vision of a self-healing city is much bigger than just concrete. Bioconcrete is a foundational piece, but it's part of a larger puzzle. The goal is to create urban environments that can adapt, respond, and repair themselves with minimal human help. We're talking about a complete paradigm shift, from a constant cycle of reactive repairs to a new era of proactive, autonomous maintenance. And this vision is being fueled by incredible innovations across materials science. Researchers are developing self-healing asphalt that uses embedded steel fibers. When you pass an induction heating machine over the road, the fibers heat up, melting the surrounding bitumen, which flows into and seals any cracks. There are self-healing polymers for coatings and components, and even self-healing metals and ceramics. Imagine windows that can fix their own scratches, or water pipes that seal their own leaks. This new generation of smart materials will work hand in hand with smart technology. We can embed sensors in our infrastructure to detect damage the moment it starts. We can then deploy fleets of autonomous drones and robots to perform repairs. One concept, called Perceive and Patch, envisions swarms of flying robots that can find, diagnose, and fix potholes on their own. By integrating these technologies, our cities will become not just more resilient, but more efficient and sustainable, conserving resources and reducing the environmental impact of urban life. The crumbling infrastructure we see in so many of our cities is a clear signal that our old way of building isn't sustainable. The endless cycle of damage and repair costs us dearly, both economically and environmentally. Bioconcrete presents a radical and brilliant alternative. It offers a future where our cities are more like living organisms, capable of healing their own wounds. It's a future where our infrastructure is more durable, more sustainable, and exists in a smarter harmony with the world around it. From the tiny bacteria acting as microscopic masons to the grand vision of a fully autonomous, self-healing city, this technology represents a profound change in how we build our world. The journey is just beginning, and the challenges are real. But with every new discovery and every successful project, we get one step closer to building a more resilient future. The age of living concrete is dawning, and with it comes the hope of cities that don't just endure, but heal, adapt, and thrive for centuries to come.